We have been discussing about using the wind energy for various purposes, for various applications, and that generally involves conversion of the kinetic energy of available in the wind into mechanical energy, and that form of energy, that is mechanical energy, can be later converted into electrical energy. So in previous lecture, it was shown with the help of Bed's theorem that the maximum conversion can be 16 by 27 of the power available in the wind, and the power available in the wind is 1/2 rho a u cube, right? U is the velocity of the wind. So this 15.26% is based on an ideal model with a linear momentum theorem, where there are many simplification assumptions. If you think of a real turbine, then there is deviation from those assumptions. So based on that, we can modify the number that is presented by the Bed's theorem, that is 16 by 27 or 59.26. So several such efforts have been done to theoretically predict the efficiency of turbine. So how does a real turbine is different from the assumptions made in the Bed's theorem? So as it is shown in the first figure A, when you are talking about the Bed's theorem, there is no effect of the presence of the actuator disk on the flow of air. Or in other words, you can say that it is assumed that the flow of air is undisturbed while the power is being tapped from that. But in case of a real turbine, let's say the one which is shown in the figure having just two blades, and it is rotating slowly. When it is rotating slowly, because of its rotation, there is at least some part of the air which is passing through this circle, right, is getting distorted or getting disturbed, as it is shown in the figure. Now, if the speed is low enough, then there could be some regions from where the air is able to pass undisturbed also. Now, if it is being rotated at an optimum speed, in that case, all air will get disturbed, as it is shown in the figure. If you rotate it at like a particular speed, you come to a point where all air is getting disturbed. Now beyond that, there may be a point where you see that on the downstream there is generation of wake, right? So the next step is ideal thing is the Bed's theorem. Then if it is rotated slowly, you see that some part of air is getting disturbed, some part is still undisturbed. The more closer thing to a practical situation is that the blade is rotated fast enough so that all air passing through that is getting disturbed. Because if you allow some air, practically seeing at the things, if you allow some air to pass through it without getting disturbed, actually it doesn't contribute to the power generation. So you should rotate it at enough speed so that it comes in contact with all the streams of air, and in that case all streams of air are going to get disturbed. And again, in a real situation, what will happen is that due to the end effects, on the downstream, there is going to be wake generation, and there will be additional drag force which will be created. So to take into account such effects, other models have been presented. So it is expressed in the form of an equation. So Gluert and others presented this equation. So Cp, the coefficient of power, is equal to 16 by 27 into exponential of minus 3538 lambda raised to minus 1.2946. Right? You don't need to remember the formula, but just understand the meaning conveyed by that formula, or what is the significance of various terms in this. So as per the Betz theorem, there is no effect of the tip speed ratio on the coefficient of power. It remains constant, whatever may be the speed of the turbine and the relative speed of the tip with respect to the wind, right? But practically that is not the case. The CP, or the efficiency of the turbine, depends upon the tip speed ratio. That is what has been even observed with the help of experiments. So Gluert presented this equation, and if you see this second term, exponential something, that is always going to be less than 1. It means that the real turbines would give you efficiency less than 16 by 27 or 0.59 or 59%. It's always going to be less than that. But what you see is higher the lambda, higher the CP. Okay, so in that so that way, higher tip speed ratio would always give you higher value of CP. But then this doesn't take into account the effect of drag, the effect of drag force. We are going to talk about this a bit more later on, where you will be shown the aerofoil, the shape used in the turbine, the cross section, and how is the lift force and the drag force are generated, and how do they contribute to the power generation. Though we are not going into the detail of the theory of aerofoil and the aerodynamics related with that, some basic idea would be given about that. So in real turbines, there is presence of the drag force also, which reduces the efficiency or the coefficient of power further. So the another equation, which is modification of the previous equation, where you have the term minus lambda into epsilon. So obviously this minus means this lambda into epsilon is a positive number. So this like deducting it from the first term is going to give you a lower value. So lambda into this epsilon always is going to give you lower value as compared to that term not being present. So lambda, you already know, it is tip speed ratio, and this epsilon is the ratio of drag coefficient and lift coefficient, CD by CL. Okay, so higher the drag force compared to the lift force, the efficiency of the turbine is going to be low. So CD should be as low as possible as compared to CL. It will never happen that it is not present at all, but the ratio should be as low as possible to have higher efficiency of a turbine or coefficient of power of the turbine. So these are the models which are presented. Coefficient of power. So as per the Betz theorem, the efficiency will always remain around 59%, right? 59.3%. And it is unaffected by the tip speed ratio. But then as per the equation given by Gluert, higher the tip speed ratio, higher the efficiency or coefficient of power. but still the limit is 59.3%. Okay, so higher the tip speed ratio, you approach that limit. So that's about an ideal propeller. An ideal propeller where you are not considering the effect of the drag forces. Then various types of turbine have been, various designs of the turbine have been tested. Let's say in the uh, in the lab. Okay. So there the shape or the characteristic or performance curves of these turbines have been plotted. So you can change the tip speed ratio, like for a given size of the turbine, if you change the wind speed, that's going to change the tip speed ratio. So those turbines can be tested and their performance curves, the real performance curves can be plotted. So for typical design, a particular design of a wind turbine has been plotted here in this chart. So you can see different turbines designs shown here: 7 years, then American multi-blade, then the Dutch 4-arm, Darius, and high-speed propeller. Right. So if you look at the 7 years and Dutch 4-arm turbines, what you find is that even the maximum efficiency is not very high. It is not even able to go beyond 20%. So these designs of the turbines is not very efficient design. We are talking about the basic design, right? If there are some some deviations from that, this is not talking about that. So the basic design of 7 years and the Dutch 4-arm gives you a very low efficiency. And what you find is that the Dutch 4-arm should rotate at a bit higher speed to get that maximum efficiency, while 7 years would rotate at low speed, should be rotated at low speed to get the higher efficiency. But then 7 years is very steep. So it means that if you don't operate it at optimum conditions, its efficiency is going to drop very fast, right? And the Dutch 4-arm is a bit flatter than that, but still the shape is not very good. Then American multi-blade gives you maximum efficiency of around 30%, but still the curve is steep, right, on either side. It means that again, if you don't operate it at optimum conditions, it's going to or optimum tip speed ratio, there will be a sharp drop in the coefficient of power for American multi-blade turbine also. Okay. Then the Darius design, you can see it is somewhat superior and it gives you efficiency approaching around 40% at the peak. And the curve is also not very steep, though it is steep as compared to the high-speed propeller type of turbine. Particularly on the right-hand side, it is not very steep. Means if you operate it at an optimum tip speed ratio, then the efficiency is highest. But then, if the tip speed ratio is bit higher, still you are not sacrificing or the drop in the efficiency is not that rapid. Okay, so that's why the Darius design is also considered to be one of the superior designs. And then the high-speed propeller is having perhaps the best characteristics and can provide you efficiency even higher than 40%, showing up to around 45%. And the curve is also flat. It means that even if you don't operate it at the optimum tip speed ratio, the drop in the efficiency is not very high. So this is the reason why the high speed propeller is the design which is the most popular, and almost all commercial wind turbines producing the electrical power have or adopted this design. And that one too, the three-bladed design is the most common even in that horizontal axis propeller type of design. So now we will mainly focus upon that design and discuss various components of that. So normally 3 blades are used. There is an optimum solidity, right? The solidity has been defined. That is the area occupied by the blades to the total cross-sectional area, right? The frontal area. So that is solidity. So that solidity generally for this design, the propeller type of design should be quite low for the best performance of the turbine, right? So that's why 3 bladed design has been adopted. One or two also are options, but they are found to be more noisy and creating more visual disturbance in addition to the 3 bladed design giving you much better stability. So now, as I stated earlier, almost all designs are 3 bladed propeller type of horizontal axis design, and multiple such uh, wind turbines, right? We normally call it wind turbines now, not windmills, because the application is not milling. So they are for power generation. So windmills or wind energy generators. So multiple of them are put up at a location where annually you get average high speed of the wind, and and those wind farms generally feed to the grid. So let's talk about various components of that turbine. So let me show you the diagram of that turbine, and then we will talk about each component, 1 or 2 lines. Of course, not much detail it will not be discussed in too much detail here. So this gives you one view of that turbine. You can consider it to be a cross-sectional view. Though kind of pictorial effect is given to that, this can be considered or can be drawn as a sketch also. So what you see different components of that, and the different components, they have given numbers to that, and which component is that has been given here at the bottom. So this 15 is nothing but the blade of the turbine, okay, which converts the kinetic energy into mechanical energy, and then they are connected with the hub, right, which is inside this cover. Then this one is the coupling, then two is the low speed shaft, right? The turbine doesn't rotate at a very high speed, so it's this one is the low speed shaft. Then the this 10 is the gearbox. So you are converting the low speed into high speed, which is suitable for a generator, which generally rotate around 1400 RPM. It depends upon the design, but basically it's a high speed generator to which you have to couple this low speed shaft. So a gearbox would be generally needed. Though in some modern designs with very complicated power electronics, gearbox can be avoided. But like talking about most of the regular design existing now, there is always some a gearbox present to increase the speed of the shaft. So then you have the high speed shaft, and then this 3 is the braking mechanism in case you need to stop the turbine in emergency and during the maintenance, and then the coupling, and then this one is the generator. 7 is the generator to which this shaft is coupled and produces electrical power, and then some controls are also required. So what you see here, there should be an anemometer here which provides you the wind velocity, and a wind vane provides you the direction of the wind. And then here you see there is a ring, which with the help of this you are able to rotate this whole part. Okay, this part, the outer cover, is called nacelle. So this whole thing, nacelle, can be rotated about the vertical axis of the tower. That is, and that rotation is called yawing, Y-A-W-I-N-G, yawing. So this is a yaw ring. That ring is yaw ring. So using on this ring, this whole portion, the top portion is about to rotate, and that is to bring the turbine blades or the plane in which it rotates should always be perpendicular to the wind direction. So wind direction is sensed by the wind vane here, and it gives you the signal. So required control mechanism is required, and that provides the signal to this yawing mechanism. And this one, this vertical thing that you find, is yaw motor, and that yaw motor like provides the required rotation to the yaw ring, and the whole thing, nacelle, along with the hub and blades, get rotated and it faces the wind. So that is yawing mechanism, and there is one more mechanism which is not seen here, and that is to rotate the blades about its own axis, and that is called pitching. Okay. So I'm going to show you two videos. For the first one, explains the conversion of the wind energy into the mechanical and electrical energy and what are the different components in the wind turbine in a very simple way. And the next one is basically a tour to a real wind turbine. Right. So I'll show you those videos, and that will explain you about various components of the wind turbine in detail. Right. So this 13 is pole. This pole, the tower, right? Tower or pole. Okay. If it is of cylindrical design, there could be other type of like tower also, but the large size wind turbines which are now being used, most of them use this tubular tower kind of design made up of steel, and it comes in multiple parts, and then they are joined together at the site. Okay, this 8 is terminal brush, and so I think I have discussed all the components. Right. 6 is the power electronic system, this one. Okay, so let me play these videos one by one.
How does a wind turbine work? You've probably seen a wind farm, but do you know how wind force is converted? How does a wind turbine work? You've probably seen a wind farm, but do you know how wind force is converted into electrical energy? We are going to show you how a wind turbine works. Each wind turbine has a wind vane at the top that indicates the wind direction. This allows the turbine to rotate on the tower and face the wind. The blades also rotate on their axis for maximum resistance. Wind force, that is, the kinetic energy contained in moving air currents, spins the blades. These are designed to fully capture its energy. They can be as long as 60 meters each and are made of very light and resistant materials for ease of movement. This is why they can produce energy even with very light winds, starting from about 11 kilometers per hour. With very strong winds, above 90 kilometers per hour, the blades are placed in the feathered position and the turbine stops spinning for safety reasons. The blades are attached to the wind turbine through the hub, which is coupled to the low-speed shaft. The low-speed shaft is given this name because it spins at the same speed of the blades, between 7 and 12 revolutions per minute. To produce electricity, it is necessary to increase the turning speed of the low-speed shaft. That is the mission of the gearbox, which raises the speed over 100 times and transfers it to the high-speed shaft. The high-speed shaft, that rotates at up to 1500 revolutions per minute, is connected to a generator. The generator converts the kinetic energy into electricity, a source of energy that is easier to transport and use. The electricity produced in the generator is conducted through the interior of the tower to the base. There, the transformer raises the voltage for transport inside the wind farm. From each turbine, alternating current is sent to the substation through underground cables. Here, the voltage is increased again to feed it into the power grid and transported to end consumers. This is how we use the wind to light cities, feed industries, schools or hospitals, or operate our household appliances in a clean and sustainable way.
Okay, now another video which basically is a tour to a actual turbine.
Of a typical wind turbine generator as found on wind farms across the world. Now, exact designs do vary, but almost all the turbines in use today are horizontal axis machines which have a 3-bladed rotor spinning in a vertical plane attached to the front of a box which we call the nacelle, after the fairing around an aircraft engine. And in this nacelle we have the generator, often a gearbox and occasionally a high voltage transformer, and the whole thing sits on top of a tower which is mostly there to keep the blades from digging a hole. We tend to class turbines by their power output and hence their physical size. Wind farms might use many sub-megawatt turbines, each producing 400, 600 kilowatts each, or a few multi-megawatt turbines producing maybe up to 3 megawatts per unit. Apart from physical scale, they are arranged a bit differently. So let's start by looking at a typical sub-megawatt model. Turbines of this...
So first, the sub-megawatt turbine, that is the turbines which have a capacity of around 400 to 600 kilowatt is being discussed.
This type are typically 25 to 45 meters tall, and at the base you will often find 2 doors. The lower door takes you into a secured compartment where we have a high voltage step-up transformer. The generator at the top of the turbine is producing about 690 volts, and this transformer converts that into several thousand volts to send it more efficiently to the substation. The main entrance to the turbine is at first floor level, and there we find the control cabinet and the base of a ladder, or a series of ladders. Often in these smaller turbines, the ladders run to a series of platforms and they change sides at each platform to give you a rest area and a bit of fall protection. Platforms are generally just wooden discs suspended inside the tower walls, and they might have a trapdoor or a set of guardrails and a gate depending on how the ladders are arranged. The main run of cables goes up the wall of the tower, dodging past any intermediate junctions, because obviously the towers can't be delivered in a single 40-meter long section. They come in 20-meter long sections that are bolted together with a lot of nuts and bolts. But as we move higher and higher through the platforms, they're getting slowly narrower and narrower, so the ladders are getting a little bit closer together. But eventually, the main cables stop being attached to the wall, and they hang freely in the center of the tower, so they can twist as the nacelle rotates to face the wind. If they twist too many times, the nacelle will spin itself around to remove the twists. But as we move up, now the cable goes through a hole in the center of each platform, and at the top of the tower we have a steel platform with a sealed trapdoor, which we call the yaw platform. Just above that we have the yaw ring with the bearings that allow the nacelle and the rotors to rotate around to face the wind. And this sealed platform acts as a...
So the yaw ring is shown here, and that is the ring about which the whole upper structure is going to rotate. and this is the cable which is carrying the electricity, right? So towards the end it is free, so because this upper part rotates, so the cable should be also able to move accordingly. And every other things described, this ladder is for the personnel to go up for the maintenance purpose. Okay.
The bit of fire protection also avoids people falling back down the tower, because at the top of the nacelle we simply have a hole for which we climb, and the nacelle in this case is a vaguely tapered tube. At the back we have the wind sensors, which give us speed and direction and allow the turbine to face into the wind and to change the angle of the blades. The nacelle itself is just a fiberglass tube. At the front we have a similar fiberglass cowl protecting the hub, which is a steel casting on which we have bolted our 3 blades, and the blades can turn or pitch so that the angle they form with the wind can be varied. Out of the back of the hub we have a shaft which leads into the gearbox, then a high-speed shaft through a brake into a generator, and that generator then supplies the electrical power, as I say, at about 690 volts all the way back down the tower to the base. And right at the back we have a cooling fan, as we're generating 500,000 watts of energy inside the nacelle. Some of that is wasted as heat, and without an efficient cooling system there is the potential for the turbine to catch fire. Now, the layout of a larger turbine is broadly similar, but some of the components are in different places. So let's start by looking at the tower section of a typical 2 megawatt turbine. Where we place the high voltage transformers in multi-megawatt turbines is a lot more variable. Quite frankly, we have a lot more room, so we can decide if they can be in the nacelle, they can be at the base of the tower, they can be on platform 1 in the basement, they can be outside in a hut. In this example, the transformer's at the top, so when we go into our door, the one thing we'll not find is a transformer. We do have the high voltage switches, this case on platform 2, but on the entrance platform we have the usual control cabinet and a lift, a little green box. And that lift will take 2 people to the top of the tower, or nearly to the top, without them having to climb the single, very, very long ladder. Almost all large turbines will just have a single run of ladder for the majority of the run up the tower. It will have a wire or a rail system, a fall arrest device fitted to it, but it is still a long slog up the ladder, which is one of the reasons why service lifts are so important. And again, the tower's in sections so that it can be delivered around the country without demolishing villages. Sometimes, if we're running a long distance and we haven't got room for a proper platform, we can put a half moon in place. No fall protection on the platform, but we assume you would keep your lanyards connected at this point because it's quite a long way down. The cable again breaks free from its mounting and hangs in the centre of the tower for the last 10-20 metres or so that it can rotate as the nacelle yaws into the wind, and the lift eventually runs out of space. Remember, the tower is getting narrower and narrower as we get to the top, so the lift tends to park itself about half a platform from the top, and we have a normal ladder which then leads to the yaw platform, and then it starts looking very much like the smaller turbine did. We have a yaw ring bolted to the underside of the nacelle, joining it to the top of the tower, series of disc brakes.
This very nicely shows the yaw ring, and this blue
and around that yaw ring,
blue cylindrical shape that you see here is the yaw motor, right, which can rotate the yaw ring.
Lock it in position when the wind isn't changing direction, and when it is, we have a series of either electric or hydraulic motors that rotate the entire mechanism around on the top of the tower. The layout of a multi-megawatt nacelle is again more variable than for a smaller version. We always have to have a generator, but we may not have to have a transformer. In a few cases, such as the famous Enercon egg-shaped nacelle, we don't even need a gearbox. They're direct drive. We just have a shaft linking to a motor, and then lots of extremely complicated electronics to condition that power for connection to the grid. But in most cases, we need the same as we needed in the small turbine: gearbox, generator, possibly a transformer, all in a fiberglass box. And in our example, we're looking at a typical design used by a number of manufacturers where we have a nacelle that's 3 meters high, 2.5 meters wide, 7 or 8 meters long. It's a fiberglass box about the size of a site hut. As before, we have our wind sensors on the roof as far away as possible from the dirty air cast off by the blades as they spin round. This design is just a fiberglass box with a flat roof. We access the roof through a couple of skylights. Some designs are like before, big cylinder with 2 opening doors. Some have an entire roof section which opens, rather like an old camper van. If we take the skin off the box, inside we have the same kind of components we had before. They're just bigger, and there's a little bit more room, so they're laid out a bit differently. The only additional component up here is those 3 green cylinders at the back. That's our high voltage transformer, which used to be at the base of the tower. Now we've removed a lot of the control systems and the hydraulic systems that would just clutter up the pretty picture. We've added in a bloke for scale, but most of the big components are still here. If we look at the very front of the nacelle, we have a couple of bearings which support the main shaft, which is a hollow tube, 50, 60, 70 centimeters in diameter. It's hollow so that we can get electrical cables in through this main shaft into the hub to drive all the control systems inside the hub. And we have a couple of pins on the first bearing that lock the main rotor in position if we need to access the hub. It's a safety feature. If you're in there and it starts rotating, it gets scary. So our main shaft drives our gearbox, which is mounted centrally because it's often the heaviest component. Out of the back comes a high-speed shaft, as before. That's where the braking system is. High-speed shaft then drives the generator, which is usually oil-filled. The generator then supplies 690 volts, in this case into our transformer, which is sitting right next to it. That high voltage signal then passes through the switchgear and the cabinets, down the dropper cable, straight down to the bottom of the tower, through those switches on platform 2 and off to the substation. And that, as an overview, is pretty much all there is to it. The only thing left to talk about are the blades, obviously, which actually do the work. We still have 3 of them. They still pitch, in other words, they twist on themselves to line up with the wind. And you access the hub through the gap between this fiberglass cowl and the cast hub. It's a bit of a wriggle, but you wriggle through, usually feet first, crawl through the hole in the middle of the hub, and inside the hub we'll find the control electronics, the pumps, the motors and the batteries to control the pitch of each blade, rotating it on its own bearing.
So now the pitching mechanism is being discussed. These 3 motors are the motors which rotate the blades about their own axis, and they are responsible for pitching motion of the blades.
To set the optimum angle for the wind. If we turn the blades through 90 degrees so they're edge on to the wind, there's no net turning force. It's a process called feathering, and the turbine will stop. Obviously there is a vast amount more going on inside a turbine, lots of wiring and control systems and lights and sensors and fire extinguishers, etc. But that is basically it, the general overview of most turbines that you find on wind farms today. Designs for the future will be significantly different, but at the moment it's a windmill on a stick.
So with the help of these 2 videos, I think you must have been able to understand the wind turbine in a very nice way, the different components, the functioning of different components, etc. Okay, now we talk a bit about how it operates, what is the working principle, etc. So first thing, that the blades have aerofoil shape. That is, if you cut the blade, this is the shape that you will see, the cross section. So it's called aerofoil shape, right? It's a special case shape developed to generate high amount of lift force as compared to the drag force. So the different terminologies of that are shown in this figure. This is the chord, right? If you join the midpoint of the leading edge and the trailing edge, then you get the chord. And then the thickness of the blade on upper side and lower side could be different. So it's upper camber and lower camber, which have different values. And the chord length. Now this is the relative wind shown, right? The velocity triangle and the force polygon, etc. will be shown in the later figures. So the wind which is striking the blade, let's say the relative wind, because the wind is having a particular direction and velocity, as well as the blade is also rotating. So we are talking about the relative wind. So this relative wind would make some angle with this chord, with the chord of the blade, and that angle is called angle of attack, and that is a very important angle, and a particular optimum value of this angle should be maintained to be able to tap the maximum power from the wind, right? So in the video it talked about the pitching of the blade. So pitching of the blade is adjusting the angle of attack so that you are able to generate optimum power at, because the wind velocity doesn't remain constant, and the direction, of course, you have yawing, which with the help of which you keep it try to keep it always perpendicular to the plane of rotation, but at least the velocity you can't do anything with that, with the speed. So you have to do the required pitching to be able to produce the maximum possible power for a given speed of the wind. Okay. And there are different commercial shapes of the aerofoils developed and used in different application. Wind turbine is of course not the only application. Okay. So now we will discuss different terminologies related with the aerofoil. Okay. So this angle of attack is already known to you, and this is the relative wind, and because of typical shape of the aerofoil, the lift force, extra lift force is generated, which should be much higher than the drag force, because generally drag force doesn't contribute to the uh, power generation in case of the wind turbine, but you want the lift force to be higher. So one would like to keep an optimum value of angle of attack. So that has been depicted with the help of three figures here. So in one case, so this relative wind, you can consider this horizontal line, and then the chord is shown, and the angle with the relative wind and the chord is the angle of attack. So in first case it is 3 degrees, in second it is shown 10, and in the third it is shown 30 degrees. So if you keep like a low angle of attack, then the lift force that you are able to generate is not very high, but at a particular angle of attack you find that the lift force is high, and the ratio of the lift force to drag force is low. But if you increase the angle too much, what you find is that the uh, there is formation of eddies, and because of that the drag force becomes too high. So that is also not desirable for optimum power generation. This case may be used for stalling purpose. That is, if you don't want, if the wind velocity is too high and you want to reduce your power production, then you might go for this, and you may increase the angle of attack so much that there is too much of dissipation of the energy, and you are not producing too much of power, because that's going to means there is a limit to the design, how much forces or how much power it can take. So there is some basics about the aerodynamics of the aerofoil, as well as the power generation using that. Okay. So now we'll talk about the force polygon that you find. Yeah, so maybe you will get the answer after discussing of this force polygon. So here, the kind of top view of the turbine is shown. So you can see this nacelle section. You can see the rotor axis, and multiple blades are connected with that, out of which one blade is shown full, the other blade is just shown, and the third blade is not seen, and the tower is also partially seen, and the rotation of the blades is shown. Yeah. So now this, if you cut this blade, you see this aerofoil shape. Now the true wind is flowing perpendicular to, or it is parallel to this axis, right? Parallel to the axis, or it is perpendicular to the plane of rotation of the blade. Now, because the blade is rotating at a certain speed or velocity, so this is the blade speed, right? This is the blade speed. Now, this polygon is actually not in this plane. You can think that this is like you rotate the blades by 90 degrees. So this will also, the whole thing will also rotate by 90 degrees. So the blade speed is shown with this green line, right? It is, you can consider it to be, let's say, moving downward, right? So that's the whole thing is in that vertical plane. So the blade speed in that case is vertically downward, right? This still remains horizontal, and this is the direction of the apparent wind, right? That's nothing but the resultant direction, the apparent wind. Then you draw this chord of the blade, and the angle made by the apparent wind with the chord of the blade is the angle of attack. Now, there are different forces generated. One force would be along the chord, right? So that is the drag force, right? That is the drag force. So parallel to the chord, the force is the drag force, and perpendicular to the chord is the lift force, right? So the force which is perpendicular to the chord, you call it lift force, and the force which is parallel to the chord, you call it drag force. And then this is the resultant force, this green line here, net aerodynamic force on the blade. Now you can resolve this force again into two parts, one which is parallel to this axis, rotor axis, and the other one is perpendicular to that, right? So the one which is parallel to this rotor axis is not going to contribute to the rotation of the blade. It is actually going to apply thrust force on the turbine, on the tower rather, right? So you need to have the design which is able to take up this thrust force, and this is responsible for producing the torque, right? This force is responsible for producing the torque, right, which is actually perpendicular to the blade and also perpendicular to the rotor axis. You can consider it to be in vertical direction because the whole thing will be rotated by 90 degrees. Okay, so that is the useful force that you are generating. Now you can see that this lift is responsible for thrust as well as torque. The lift is responsible for thrust as well as torque. So it's the main force which is helping you to produce this torque. But the side effect is this thrust force also, which is also sizable. Drag force, if you see, it's actually reducing your it's contributing to the thrust force, but it is actually reducing the torque, right? It is in the opposite direction. If you resolve it into two components, the horizontal and vertical, you will see that it is actually opposing this force, right, which is producing the torque, and it is helping the thrust. So drag force should be as low as possible, and lift force, you have to have a high value of lift force if you want to get high torque. So this is a very basic explanation about a particular design of wind turbine, right? We are actually not going into too much detail of the aerodynamics of that. That's actually not the subject of discussion here. But when you talk about this particular design of the windmill, you need to have some basic idea about how the power is generated and which are the forces generated, and that is finally going to affect the design or considerations for the design of a wind turbine, right? So that's the reason we discussed those things it's a very basic or preliminary discussion on that, how different forces are acting, and that how the power is generated, that is kinetic energy is converted into mechanical energy, which is fed to the generator, and you get the electrical power. Yeah. So the blade, the rotational speed of the blade V is nothing but R into the angular velocity, and the relative velocity of the wind may be written as VR, and then you produce the drag force and you produce the axial force, rather you produce the drag force and you produce the lift force, which can be resolved into the axial component and the component which is producing the power, FP. Right, so this one you can call FA, the thrust force, axial, and this is FP, which is responsible for power generation. Okay. And finally, the mechanical power that you generate is Cp into the power in the wind, and like 2 pi nt is the power that you generate. And if you're talking about electrical power, then you have to also multiply the efficiency of the generator, which gives you the overall efficiency, right? And if you want to like also include the efficiency of the coupling, then even that efficiency will come into picture. Okay, so with this we end today's lecture.